Hello there, and welcome to the Sleepy Science channel. I'm so glad you're here. Maybe it's been a long day, or maybe you just like to fall asleep thinking about stars, galaxies, and the quiet mysteries of the universe. If you're settling in for the night, maybe your thoughts are still restless, still turning over the small things or the big ones. That's perfectly natural. There's no hurry. You don't need to do anything right now except let yourself be here, breathing quietly, eyes closed or nearly closed, and allow your mind to wander somewhere else for a while. Somewhere vast and gentle, somewhere that asks nothing of you except to listen, and even that you can let go of whenever you're ready. Tonight, we're going to drift together through the cosmos. Not the cosmos of equations or textbooks, but the one that exists all around you right now, even if you can't see it. The one that hums quietly in the darkness above your roof, stretches beyond the atmosphere, and unfolds into distances so immense that they lose all meaning except as feelings. Awe, maybe. Or calm. Or the soft comfort of knowing that you are part of something unimaginably large, and that it's okay not to understand it all. We'll be exploring cosmology tonight, the study of the universe as a whole, its origins, its structure, its fate, and all the mysteries that sit quietly at the edge of what we know. These are questions that have puzzled scientists for generations, and many of them remain unanswered. But that's part of what makes them so restful to think about. There's no test at the end, no right answer you need to memorize, just the gentle unfolding of ideas, images, and possibilities, each one a little doorway into wonder. So let your shoulders drop, let your jaw unclench, let your breathing slow down to its own rhythm, and know that you can drift off at any moment. This story will keep going whether you hear it or not. It's here to accompany you, not to demand your attention. And if these quiet journeys into science and space help you rest, then that's all they need to do. Let's begin by stepping outside, at least in your mind. Imagine it's a clear night, no clouds, no city lights, just you and the sky. Above you, stars scatter across the darkness, like salt spilled on a black cloth. Some of them are nearby, cosmically speaking. Others are so far away that their light has been traveling towards you for thousands of years, maybe longer. You're seeing them not as they are, but as they were, long before you were born. And if you could see even further, past the stars, past the glowing band of the Milky Way, you'd begin to notice something else. Faint smudges of light that aren't stars at all. Galaxies. Entire islands of billions of stars, so distant that they blur together into soft glowing patches. Some of them are spirals, like ours. Others are elliptical or irregular, or strange in ways we're still trying to understand. And beyond those galaxies, there are more. And beyond those, more still. The universe, as far as we can tell, is filled with galaxies, stretching out in every direction, as far as our telescopes can see. But what holds it all together? What shapes it? And where did it all come from? These are the questions cosmology tries to answer. And the answers, when we have them, are often stranger and more beautiful than anything we might have imagined. You don't need to sit up or open your eyes to picture this. Just let the image rest gently in your mind. A universe full of light and motion, expanding slowly, cooling gradually, and carrying within it the memory of its own beginning. You're lying here, on a small planet, orbiting an ordinary star, in the outer arm of a spiral galaxy, in a universe that's about 13.8 billion years old. That number is almost too large to hold in your head, and that's okay. You can let it blur. You can let all the numbers blur. What matters is the feeling, the sense of scale, the quiet recognition that you are very small and the universe is very large, and somehow both of those things are comforting. Let's start with something simple, something you can almost feel. The ground beneath you. It feels solid, doesn't it? Unmoving. But that's an illusion. Right now, as you lie still, you are moving. The Earth is spinning on its axis, carrying you eastward at over 1,000 kilometers per hour. You don't feel it because everything around you is moving with you. The air, the walls, the bed, all of it turning together in a smooth, unbroken motion. But that's not the only motion. The Earth is also orbiting the Sun, tracing a long ellipse through space at about 30 kilometers per second. And the Sun itself is moving, orbiting the center of the Milky Way galaxy at over 200 kilometers per second. And the Milky Way is moving too, falling slowly toward the Andromeda galaxy, and drifting along with a larger flow of galaxies towards something even more distant, something massive and mysterious that astronomers call the Great Attractor. You are moving, even now, even as you rest. Carried along by invisible forces on a journey you didn't choose and can't control. And somehow, that's okay. It's even peaceful, because motion on these scales doesn't feel like motion. It feels like stillness. A deep, cosmic stillness where everything drifts together, slowly and calmly, through the dark. Now, let's pull back a little further. Imagine you could rise up, not physically, but in your mind's eye, rising above your city, your country, your planet. You'd see the Earth below you, blue and white and fragile, turning slowly in the blackness. And around it, nothing. Just empty space, scattered with a few neighboring planets, the moon, and the distant sun. But that emptiness is deceptive. Space is not truly empty. Even in the darkest, quietest regions between stars, there are things. Thin clouds of gas, stray atoms of hydrogen drifting alone. And something else, something we can't see but know is there. Dark matter, an invisible substance that makes up most of the mass in the universe, and yet doesn't emit, absorb, or reflect light. It's all around you, passing through you right now. Trillions of particles every second, and you'll never feel a single one. Dark matter is one of the great mysteries of cosmology. We know it exists because we can see its effects. Galaxies spin too fast to hold together based on the visible matter alone. Light from distant objects bends more than it should as it passes through space, as if deflected by invisible mass. And the large-scale structure of the universe, the way galaxies cluster and form vast cosmic webs, only makes sense if there's far more matter out there than we can see. But what is it? We don't know. It could be a new kind of particle, something that interacts only through gravity. Or it could be something stranger, something that challenges our understanding of physics itself. Scientists have built detectors deep underground, shielded from cosmic rays and other interference, waiting patiently for a dark matter particle to collide with an ordinary atom. So far, nothing. Just silence. But the search continues, slow and steady, like all good science. And while they search, the dark matter keeps doing what it's always done, holding galaxies together, shaping the structure of the cosmos, moving invisibly through the night, through your walls, through your body, as silent and untouchable as a thought. Let your breath slow down a little more. There's no need to hold on to these ideas tightly. Just let them pass through you the way dark matter does. You can picture it if you like, a faint mist of invisible particles drifting through the room, through the earth, through everything. Or you can let the image dissolve and simply rest in the feeling of it, the quiet presence of something vast and unseen. Always there, always moving, always beyond our reach. Now, if dark matter is the invisible scaffolding of the universe, then dark energy is its invisible engine. And this is where things get even stranger. For most of the 20th century, scientists assumed that the universe was expanding, yes, but slowing down. After all, gravity pulls things together. So it made sense that the expansion, which began with the Big Bang, would gradually lose speed over time, like a ball thrown into the air slowing as it rises. But in the late 1990s, astronomers made a startling discovery. They were studying distant supernovae, exploding stars that can be used as cosmic measuring sticks, and they noticed something unexpected. The universe wasn't slowing down, it was speeding up. The expansion of space was accelerating, driven by some unknown force that seemed to push against gravity itself. They called this force dark energy, and it now appears to make up about 68% of the total energy in the universe. That's more than dark matter, more than ordinary matter, more than everything we can see, or touch, or measure directly. And we have no idea what it is. Some physicists think it might be a property of empty space itself, a kind of energy that emerges from the quantum foam, the restless fluctuations that happen even in a vacuum. Others think it might be a new field, something like the Higgs field, but spread throughout all of space and time. Still others wonder if our equations are simply wrong, if gravity behaves differently on cosmic scales than we think. Whatever it is, dark energy is gently, steadily, invisibly pushing the universe apart. Galaxies that are far away from us are receding faster and faster, and if this continues, and most evidence suggests it will, then the universe will keep expanding forever. Stars will grow farther apart. Galaxies will drift into isolation. And eventually, trillions of years from now, the night sky will grow dark and empty, with only a few nearby stars visible and nothing beyond. But that's a long way off. For now, the universe is still bright, still full of structure and motion, still young enough, in cosmic terms, to surprise us. You can let your mind rest on that image for a moment, if you like. A universe growing larger, gently and endlessly, like a slow exhalation that never quite finishes. Or you can let it go entirely and simply notice the feeling of your own breath, slow and steady, as you sink a little deeper into rest. Let's talk about the beginning now. Or at least what we think was the beginning, about 13.8 billion years ago. The universe as we know it began. Not with an explosion in space, but with the sudden appearance of space itself. Time, matter, energy, all of it emerging from a state so hot and dense that our current laws of physics break down. We call this event the Big Bang, though that name is a little misleading. There was no bang, no sound, no center, just a rapid expansion of space, carrying energy and particles with it, cooling as it grew. In the first fraction of a second, the universe was unimaginably small and hot. Smaller than an atom, hotter than anything we can create in a laboratory. But it was also expanding, faster than the speed of light. Not because anything was moving through space that quickly, but because space itself was stretching, inflating, in a process we now call cosmic inflation. This inflationary period lasted less than a trillionth of a second. But in that brief moment, the universe grew by a factor of at least 10 to the 26. Tiny quantum fluctuations, random blips in the fabric of space and time, were stretched to cosmic proportions. And those fluctuations became the seeds of everything we see today. The slight variations in density that would eventually grow into galaxies, stars, planets, and people. After inflation ended, the universe kept expanding, but more slowly. It was still incredibly hot, a roiling sea of particles and energy, too dense for light to travel freely. Photons, the particles of light, would scatter off electrons almost immediately, like trying to see through a thick fog. But as the universe expanded, it cooled. And after about 380,000 years, it reached a critical point. The temperature dropped low enough for electrons to combine with protons and form the first atoms, mostly hydrogen and helium. Suddenly, the fog cleared. Light could travel freely for the first time, and the universe became transparent. That light is still traveling today. We call it the cosmic microwave background, and it's the oldest light we can observe. It comes from every direction, a faint glow filling all of space, cooled by billions of years of expansion into microwaves. When we map it, we see a nearly uniform temperature with tiny variations, less than 1 part in 100,000. But those tiny variations are incredibly important. They're the fingerprints of the early universe, the faint echoes of the density fluctuations that would later grow into the cosmic web of galaxies. You don't need to picture all of this in detail. Just let the idea settle gently. The universe, once small and hot and opaque, now vast and cool and transparent. A long, slow unfolding from simplicity to complexity. From a featureless glow to a cosmos filled with stars and worlds and the quiet mystery of consciousness. And you, lying here, are part of that story. The atoms in your body were not made in the Big Bang. They were forged later in the cores of stars, scattered into space when those stars died, and gathered again into planets and life. You are made of stardust, as the saying goes. But more than that, you are made of time. Billions of years of cosmic history, compressed into this single moment, this single breath. Let that thought rest with you. Or let it go. Either is fine. Now, let's drift a little further into the mystery. Because as much as we've learned about the universe, there's still so much we don't understand. And some of the biggest questions are also the simplest. Why is there something instead of nothing? Why does the universe exist at all? Why is it the way it is? With these particular laws of physics? These particular balance of matter and energy? And why, in a universe that should have been born with equal amounts of matter and antimatter, do we see only matter now? Where did all the antimatter go? These are deep questions, the kind that scientists and philosophers have wrestled with for centuries. And while we've made progress, we're still far from answers. But that's okay. Not knowing is part of the journey. And in the quiet of the night, not knowing can feel almost comforting. A reminder that the universe still has secrets, still holds space for wonder. Take the question of matter and antimatter, for example. According to our current understanding of physics, the Big Bang should have created equal amounts of both. Matter, the stuff that makes up stars and planets and people. And antimatter, which is almost identical to matter except that when the two meet, they annihilate each other in a burst of pure energy. If the universe had started with equal amounts, then all the matter and antimatter should have destroyed each other almost immediately, leaving behind nothing but light. But clearly that didn't happen. We're here. The stars are here. Matter won, somehow. But we don't know why. There are theories, of course. Some physicists think there might be a subtle asymmetry in the laws of physics, a tiny preference for matter over antimatter that tipped the balance. Others wonder if antimatter might still be out there somewhere, in distant regions of the universe we can't see. Still others suggest that the answer might lie in processes we don't yet understand, involving exotic particles or new forces. The truth is, we don't know. And that's okay. The universe is patient. It's been holding this secret for nearly 14 billion years. It can wait a little longer. You can let your thoughts drift now, if they haven't already. Let the questions blur into the background, like distant stars fading as your eyes grow heavy. There's no need to solve anything tonight. No need to understand. Just the gentle flow of ideas, washing over you like waves on a shore. Each one a little softer than the last. Let's talk about something even stranger now. The shape of the universe itself. When we think about shape, we usually imagine something with edges, with boundaries. A sphere, a cube, a plane stretching out flat. But the universe doesn't seem to have edges, at least not in the way we'd expect. You can't travel to the edge of space and find a wall or a border. Instead, space might curve back on itself, or it might stretch on forever, infinite in all directions. According to Einstein's theory of general relativity, the shape of space is determined by the matter and energy it contains. Mass and energy curve space-time. And that curvature is what we experience as gravity. On small scales, like around the Earth or the Sun, this curvature is gentle, but on cosmic scales, the curvature can add up, bending space in ways that affect the entire universe. So what shape is the universe? We don't know for sure, but current observations suggest it's very close to flat. Not flat like a piece of paper, but flat in a more abstract sense, meaning that parallel lines stay parallel, and the angles of a triangle add up to 180 degrees, even over cosmic distances. If the universe is perfectly flat, then it's probably infinite, stretching on forever in all directions. If it's slightly curved, then it might wrap back on itself, like the surface of a sphere. You could, in theory, travel in a straight line and eventually return to where you started, not because you hit an edge and turned around, but because space itself loops. And if the universe has negative curvature, then it's shaped more like a saddle, curving away from itself, also infinite, but in a different way. We may never know for certain which of these is true. The universe is so vast, and our observations are so limited that the curvature, if it exists, might be far too gentle for us to measure. But that's okay. The universe doesn't need us to know its shape in order to exist. It simply is, vast and quiet and indifferent to our questions. You can picture it if you like. A gentle curving surface, stretching out in all directions, carrying galaxies along with it, like leaves on a slow-moving river. Or you can let the image fade and simply rest in the not knowing. Sometimes, not knowing is its own kind of peace. Let your body soften a little more. Let your thoughts slow down, like a stream that's finding its way to stillness. There's no hurry, no destination, just this quiet drifting, this gentle unfolding of the cosmos in your mind, and the even gentler unfolding of sleep, waiting patiently for you to let it in. We'll keep going, but more slowly now, more softly. Because the universe, for all its vastness, is also a place of stillness. And in that stillness, there's room for rest. Now let's drift towards something that sits at the very edge of understanding. Black holes. These are regions of space where gravity has become so strong that nothing, not even light, can escape. They form when massive stars collapse at the end of their lives, their cores crushed under their own weight until they become infinitely dense, at least according to our equations, a point of infinite density, called a singularity, wrapped in an invisible boundary called the event horizon. If you could approach a black hole and somehow survive the journey, you'd notice something strange. Time itself would begin to slow down. The closer you got to the event horizon, the more time would stretch and distort. To someone watching from far away, you'd appear to move more and more slowly, your clock ticking at a glacial pace, and if you crossed the horizon, you'd vanish from their view entirely, frozen at the edge of the black hole forever. At least from their perspective. But from your perspective, time would feel normal. You'd cross the event horizon without noticing anything special, at least not at first. And then, inevitably, you'd be pulled toward the singularity at the center. There's no escape, not because you're moving too slowly, but because inside the event horizon, all paths lead inward. Space itself is so curved that there's no direction you can travel, no speed you can reach that will take you back out. It's a one-way journey into the unknown. What happens at the singularity, we don't know. Our current theories break down there. General relativity predicts infinite density and infinite curvature. But infinity is usually a sign that we're missing something, that our equations are incomplete. Many physicists believe that quantum effects, which we don't yet fully understand, become important at such extreme scales. Perhaps the singularity isn't really a point, but something else? A quantum knot, a tiny region of space where the rules change. Or perhaps something even stranger, something we don't have words for yet. Black holes also raise deep questions about information. In quantum mechanics, information is never truly destroyed. It can be scrambled, hidden, transformed, but not erased. And yet, if you throw something into a black hole, it seems to disappear forever. The information it carried, the details of its quantum state, appears to be lost. This puzzle is known as the black hole information paradox, and it's been troubling physicists for decades. Some think the information is preserved somehow, encoded on the event horizon, or released slowly through a faint glow called Hawking radiation. Others think the paradox points to a flaw in our understanding of quantum mechanics, or gravity, or both. We don't have an answer yet, but the question itself is fascinating because it sits at the intersection of two of our deepest theories, general relativity and quantum mechanics, two frameworks that describe the universe beautifully on their own, but don't quite fit together. Finding a theory that unifies them, a theory of quantum gravity, is one of the great goals of modern physics, and black holes, strange and extreme as they are, might hold the key. You don't need to solve this tonight. You don't need to hold on to any of it. Just let the ideas pass through like shadows drifting across a wall. Black holes, singularities, event horizons, information paradoxes. Strange words for strange things, all of them pointing toward the same truth. The universe is deeper than we know, and that's okay. It's even beautiful. Let your breathing deepen now. Let your muscles go slack, one by one. There's nothing to figure out, nothing to remember. Just the quiet presence of mystery and the even quieter presence of rest, waiting for you to let go. Let's talk about something lighter now, at least in a certain sense. The cosmic web. If you could step back and look at the universe on the largest scales, you'd see something remarkable. Galaxies aren't scattered randomly through space. Instead, they cluster together, forming long filaments and sheets, with vast empty regions, called voids, in between. These filaments stretch for hundreds of millions of light years, connecting clusters of galaxies like threads in a web. And at the intersections, where filaments meet, you find superclusters, enormous concentrations of galaxies, some of the largest structures in the universe. This pattern is called the cosmic web, and it's shaped by dark matter. In the early universe, dark matter clumped together under its own gravity, forming a network of dense filaments. Ordinary matter, the stuff that makes up stars and planets, followed along, falling into the gravitational wells created by the dark matter and collecting in the densest regions. Over billions of years, this process created the large-scale structure we see today. What's striking about the cosmic web is how organized it is. Despite the chaos of individual galaxies colliding, stars exploding, and black holes merging, the overall structure is remarkably smooth and regular. It looks almost biological, like the neural networks in a brain or the mycelium of a fungus spreading through soil. Of course, there's no connection between these things. The resemblance is purely structural, a coincidence of how networks form when shaped by simple rules. But it's still quietly beautiful to consider. The largest structure we know, and the most complex structures we know, shaped by entirely different forces, and yet ending up with similar patterns. The cosmic web also tells us something about the history of the universe. By studying how galaxies cluster, how filaments connect, and how voids form, we can test our models of cosmic evolution. We can see if the distribution of matter matches what we'd expect from the Big Bang, from inflation, from dark matter and dark energy. And so far it does. The universe, as strange as it is, seems to follow rules. And those rules, patient and persistent, have woven the cosmos into something vast and interconnected. You can picture it if you like. A great web of light, stretching across the darkness, with galaxies glowing like dewdrops on invisible threads. Or you can let the image fade and simply rest in the feeling. Connection. structure. A universe that, for all its emptiness, is never truly alone. Let yourself sink a little deeper now. Let the weight of your body press gently into the bed. Let your thoughts slow down, drifting like clouds across a quiet sky. There's no need to hold on to anything. The cosmic web will still be there, vast and patient, whether you're awake or asleep. Now, let's turn to something even more speculative. The multiverse. The idea of the multiverse is simple, at least in concept. What if our universe isn't the only one? What if there are others, perhaps infinitely many, each with its own laws of physics, its own history, its own structures? This idea has appeared in science fiction for decades, but in recent years, it's also entered serious scientific discussion, emerging from several different areas of physics. One version comes from cosmic inflation, the rapid expansion that happened in the first fraction of a second after the Big Bang. In some models of inflation, the process doesn't happen just once. Instead, it happens over and over in different regions of space, creating a vast landscape of bubble universes, each one expanding and cooling into its own cosmos. Our universe would be just one bubble among countless others, separated by vast distances, or perhaps by barriers we can't cross. Another version comes from quantum mechanics. In the many-worlds interpretation, every quantum event splits the universe into multiple branches, each one representing a different outcome. In one branch, you're reading this right now. In another, you fell asleep 5 minutes ago. In another, you never started listening at all. These branches don't interact, but they all exist, a vast tree of possibilities growing from every quantum choice. Still another version comes from string theory, which suggests that the fundamental building blocks of reality aren't particles, but tiny vibrating strings. Depending on how these strings vibrate and how the extra dimensions of space are curled up, you could get different laws of physics, different particles, different forces. And if there are many ways for this to happen, then there might be many universes, each one with its own unique set of rules. Are any of these ideas true? We don't know. The multiverse, by its nature, is incredibly difficult to test. If other universes exist, they might be completely inaccessible to us, beyond any possible observation. Some scientists argue that this makes the multiverse untestable, and therefore not really science. Others think it's a natural consequence of our best theories, and that dismissing it would be premature. What's interesting, though, is what the multiverse might explain. One of the puzzles of cosmology is why our universe seems so finely tuned for life. The constants of nature, the strength of gravity, the mass of the electron, the rate of cosmic expansion, all of these seem to fall within a very narrow range that allows for stars, planets, and complex chemistry. If any of them were slightly different, the universe might be lifeless, or even formless, collapsing immediately or expanding so fast that nothing could ever form. In a multiverse, this tuning might not be so surprising. If there are countless universes, each with different constants, then of course we find ourselves in one where the constants allow for life. We couldn't exist in the others. It's a bit like asking why we live on a planet with breathable air. Not because the universe was designed for us, but because we could only arise in a place that happens to support us. This idea is called the anthropic principle, and it's controversial. Some find it elegant and explanatory, Others find it unsatisfying, a way of giving up on finding deeper reasons. But either way, it's a reminder that our existence might be, in some sense, a coincidence, not meaningless, but not inevitable either. Just one possibility among many, quietly unfolding in a corner of the cosmos. You can let that thought rest with you, or let it dissolve. The multiverse, if it exists, is so far beyond our reach that it changes nothing about your life right now. You're here, in this universe, in this moment, breathing slowly, drifting gently, and that's enough. Let's slow down even more now. Let's talk about time. Time is something we take for granted. It flows, we move through it, and it carries us from past to future. But according to relativity, time is not absolute. It can stretch, slow down, or even stop, depending on how fast you're moving or how strong the gravity around you is. We've already touched on this near black holes, where time slows to a crawl, but the same effect happens, more gently, everywhere. Time runs slightly slower on the surface of the Earth than it does in orbit, because the Earth's gravity, though weak, is still enough to bend space-time. GPS satellites have to account for this. Their clocks run faster than clocks on the ground, and if we didn't correct for it, the system would quickly become inaccurate. On cosmic scales, time becomes even stranger, because the universe is expanding, and because that expansion affects how light travels. Distant galaxies exist in a kind of shifted time. When we look at a galaxy a billion light years away, we're seeing it as it was a billion years ago. Its light has been traveling toward us all that time, and in the meantime, the galaxy itself has aged, changed, perhaps even merged with another galaxy, or faded into darkness. There's also the question of whether time had a beginning. Most cosmological models say yes. Time, like space, emerged with the Big Bang. Before that, if before even makes sense, there was no time, no change, no sequence of events. Just a kind of timeless quantum state, perhaps, or nothing at all. But some models suggest otherwise. In cyclic cosmologies, the universe goes through endless cycles of expansion and contraction, with time stretching infinitely into the past and future. In others, time might be an emergent property, something that arises from deeper, timeless laws. We don't know, and perhaps we can't know. Time, like so many things in cosmology, might be beyond our full understanding, but that's okay. You don't need to understand time to experience it. And right now, time is slowing down for you. Your thoughts are softening. Your awareness is fading. And soon, time might stop mattering altogether, at least for a while. Let yourself drift now. Let the ideas fade into the background. Time, space, black holes, multiverses, all of it gently dissolving, like mist in the morning sun. You don't need to hold on to any of it. Just let it go. Let's return to something closer, something you can almost touch. The stars. On a clear night, when you look up at the sky, you might see a few thousand stars if you're somewhere dark, away from city lights. Each one of those points of light is a sun, much like ours, burning through nuclear fusion, converting hydrogen into helium and releasing energy in the process. Some are smaller and cooler than our sun, glowing red and dim. Others are massive and hot, blazing blue-white, burning through their fuel at an astonishing rate. But what you're seeing is only a tiny fraction of what's out there. Most stars are too faint or too distant to see with the naked eye. Our galaxy alone contains somewhere between 200 and 400 billion stars, and there are at least 2 trillion galaxies in the observable universe, each with billions or even trillions of stars of their own. The numbers become meaningless after a while, too large to grasp, too vast to hold in your mind. But here's something gentler to consider. Every star you can see in the night sky, every single one, is part of our own galaxy, the Milky Way. Even the faintest stars visible to your eye are relatively nearby, cosmically speaking, just a few thousand light years away at most. The more distant parts of our galaxy are too faint to see as individual stars, and other galaxies, with all their billions of suns, appear only as dim smudges, if they appear at all. This means that when you look at the night sky, you're seeing your neighborhood, your stellar community. These are the stars that share our corner of the universe, all of us drifting together through space, orbiting the galactic center, held together by gravity and time. And among those stars, scattered through the darkness, are planets. Thousands of them have been discovered so far, orbiting other suns. Some are gas giants, larger than Jupiter. Others are rocky worlds, perhaps with mountains and valleys, and maybe even oceans. A few orbit in what we call the habitable zone, the region around a star where temperatures might allow for liquid water on the surface. We don't know if life exists on any of these worlds. We haven't found it yet. But the sheer number of planets suggests that it's possible. There are so many stars, so many worlds, that even if life is rare, it might still be out there somewhere, looking up at its own night sky, wondering if it's alone. Or perhaps life is common. Perhaps the universe is filled with it, from simple microbes clinging to rocks, to complex ecosystems, to intelligent beings building telescopes and asking the same questions we ask. We simply don't know yet, and in the quiet of the night, that uncertainty can feel almost hopeful. The universe is so vast, so full of possibility, that anything seems imaginable. You can let that thought rest with you. The idea that somewhere, out among the stars, there might be others. Or the idea that we might be alone, unique, a single flowering of awareness in an otherwise silent cosmos. Both possibilities are profound. Both carry their own kind of beauty. Let your breathing slow down even more now. Let your body settle deeper into stillness. There's no need to choose between these ideas, no need to decide what's true. Just let them drift through your mind like stars across the sky, each one a small point of light, distant and calm. Now, let's talk about something that connects all of this. The elements, everything you see around you, everything you touch, everything you are, is made of atoms. And every atom heavier than hydrogen and helium was made inside a star. The carbon in your cells, the oxygen you breathe, the calcium in your blood, all of it was forged in the nuclear furnaces of stars, then scattered into space when those stars died. In the cores of stars, temperatures and pressures are so extreme that atomic nuclei can fuse together. Hydrogen fuses into helium, releasing energy and keeping the star shining. As the star ages and its core grows hotter, helium fuses into carbon and oxygen. In the most massive stars, the process continues, building heavier and heavier elements. Carbon into neon, neon into magnesium, all the way up to iron. But iron is where fusion stops being efficient. Fusing iron doesn't release energy, it consumes it. So when a massive star builds up an iron core, it's reached the end of the line. The core can no longer support itself against gravity. And in a sudden, catastrophic collapse, the star explodes in a supernova, one of the brightest events in the universe. That explosion does two things. First, it scatters the elements the star created across space, seeding the surrounding region with the raw materials for new stars, planets, and eventually life. And second, in the intense heat and pressure of the explosion itself, even heavier elements are created. Gold, platinum, uranium, all forged in the final moments of a dying star. These elements drift through space, mixing with clouds of gas and dust, and over time, they collect into new systems. Our own solar system formed this way about 4.5 billion years ago, from a cloud that contained the debris of countless earlier stars. The Earth and everything on it is made of recycled stardust. You are made of atoms that were once inside other stars, scattered across the galaxy, then gathered here on this small world and assembled into the intricate structure of a living being. It's a humbling thought, and also a connecting one. You are not separate from the universe. You are a part of it, made of the same substance, shaped by the same forces, born from the same ancient processes that created the stars themselves. Let that sink in gently. You don't need to think about it too hard. Just let it rest there, a quiet truth beneath everything else. You are stardust. The universe looking back at itself. Now, let's drift towards something stranger again. Dark energy. We've talked about it before, but it's worth returning to because it's one of the deepest mysteries we face. Dark energy is the name we give to whatever is causing the universe to expand faster and faster. It makes up about 68% of the total energy in the universe, and yet we have almost no idea what it is. One possibility is that dark energy is a property of space itself. According to quantum field theory, even empty space isn't truly empty. It's filled with fluctuating fields, virtual particles popping in and out of existence, a kind of background hum of energy. This is called vacuum energy, and in theory, it could exert a pressure that pushes space apart. The problem is when physicists try to calculate how much vacuum energy there should be, they get an answer that's wildly wrong. Off by a factor of 10 to the power of 120, one of the largest discrepancies between theory and observation in all of science. Something is clearly missing from our understanding. Another possibility is that dark energy is not constant, but changing over time. Maybe it's a field that's slowly evolving, or maybe it's the result of some other process we haven't discovered yet. If that's true, then the fate of the universe might be different from what we expect. Instead of expanding forever at an accelerating rate, the expansion might slow down, or even reverse. Or it might accelerate faster and faster, eventually tearing galaxies, stars, planets, even atoms apart in what's sometimes called the Big Rip. But these are distant concerns, if they're concerns at all. The Big Rip, if it happens, is trillions of years away. And the slow fade of the universe into darkness, the so-called heat death, is even farther off. For now, the universe is still young, still bright, still full of stars and galaxies, and the quiet unfolding of cosmic evolution. You don't need to worry about the end. Not tonight, not ever, really. The universe will take care of itself, slowly and patiently, over timescales so vast that they lose all meaning. And you, here now, can simply rest in the present moment, letting the future stay where it belongs, far away and unformed. Let your thoughts drift away from endings now. Let them drift towards something gentler. The quiet beauty of the cosmos as it is right now. Galaxies spinning slowly through the dark, stars burning steadily, planets orbiting, moons rising and setting, and somewhere on a small blue world, you breathing softly, letting go. Let's talk about light for a moment. Light is strange. It's both a wave and a particle, depending on how you look at it. It travels at the fastest speed possible in the universe, about 300,000 kilometers per second, and it never experiences time. From the perspective of a photon, if such a thing makes sense, its journey from a instantaneously. No time passes. It simply is emitted and absorbed in the same timeless moment. But from our perspective, light takes time to travel. The light from the sun takes about 8 minutes to reach Earth. The light from the nearest star, Proxima Centauri, takes just over 4 years. The light from the Andromeda galaxy takes 2.5 million years. And the light from the most distant galaxies we can see has been traveling for over 13 billion years, almost as long as the universe has existed. This means that when we look out into space, we're also looking back in time. The farther we look, the older the light, and the younger the universe. With powerful telescopes, we can see galaxies as they were billions of years ago, in the early stages of cosmic evolution, when stars were just beginning to form, and the universe was still finding its shape. And there's something even stranger, because space itself is expanding. Some of the light we see has been stretched along the way. Its wavelength has grown longer, shifting from visible light into infrared, or even radio waves. This is called redshift, and it's one of the key pieces of evidence for the Big Bang. The more distant a galaxy, the more its light is redshifted, which tells us not only how far away it is, but also how fast the space between us and it is growing. In this way, light is a messenger. It carries information across vast distances, telling us about the temperature of stars, the composition of planets, the motion of galaxies, and the history of the universe itself. And it does so silently, patiently, traveling for billions of years, just to reach our eyes for a single fleeting moment. You can picture it if you like. Light streaming through the darkness, crossing unimaginable distances, bringing news of distant worlds. Or you can let the image fade and simply notice the soft darkness behind your eyelids, the gentle absence of light that means rest and quiet, and the slow approach of sleep. Let your body go completely slack now. Let your mind soften. There's no need to follow every word, no need to hold on to any idea. Just let it all wash over you, gentle and formless, like water lapping at the shore. Now, Let's think about gravity one more time, but from a different angle. Gravity is the weakest of the four fundamental forces. It's much, much weaker than electromagnetism, or the strong nuclear force, or the weak force. And yet, gravity shapes the universe. It holds planets in orbit, binds stars into galaxies, and curves the fabric of space-time itself. Why is gravity so weak? We don't know. Some physicists think it might be leaking into extra dimensions beyond the three of space and one of time that we experience. In these theories, the full strength of gravity is spread across multiple dimensions, and we only feel a small fraction of it in our own. Others think gravity's weakness is just a feature of the universe, not a bug. If gravity were stronger, stars would burn out faster, galaxies would collapse, and the universe might be very different, perhaps too unstable for life. But there's also a deeper mystery. Gravity, as described by Einstein's general relativity, doesn't fit well with quantum mechanics. The two theories work beautifully in their own domains, but when you try to combine them, you run into problems. Infinities appear in the equations. Predictions break down, and we're left with the uncomfortable realization that our two best theories of the universe are, in some fundamental way, incomplete. Finding a theory of quantum gravity, a way to describe gravity at the smallest scales, is one of the great unsolved problems in physics. There are candidates, string theory, loop quantum gravity, and others, but none have been confirmed. We're still searching, still trying to understand how space-time behaves when it's bent and twisted on the scale of atoms and particles. And maybe we'll never find the answer. Maybe the universe keeps some secrets. Or maybe someday someone will have an insight, a moment of clarity, and the pieces will fall into place. Either way, the search continues, quiet and patient, like all good science. You don't need to search for anything tonight. You don't need to solve anything. Just let these ideas drift past, like clouds across the sky. Gravity, quantum mechanics, extra dimensions, all of it distant and abstract, and none of it more important right now than the simple fact that you're here, breathing, resting, letting go. Let's turn to something a little more immediate. The moon. Our moon is unusual, as moons go. It's large relative to the size of Earth, much larger than most moons compared to their planets. And it's thought to have formed in a violent collision early in Earth's history, when a Mars-sized object smashed into our young planet, sending debris into orbit. Over time, that debris collected and cooled, forming the moon we see today. The moon has been slowly drifting away from Earth ever since, at a rate of about 3.5 centimeters per year. It's a tiny amount, but over billions of years it adds up. Long ago, the moon was much closer, and the days were much shorter. The moon's gravity pulls on Earth's oceans, creating tides, and those tides, in turn, transfer energy and slow Earth's rotation. The result is that our days are gradually getting longer, and the moon is gradually receding. One day, far in the future, the Earth and moon will become tidally locked, always showing the same face to each other, just as the moon already shows the same face to us. But that's billions of years away, and by then, the sun will be nearing the end of its life, swelling into a red giant, and the Earth, if it still exists, will be a very different place. For now, the moon is still there, still rising and setting, still pulling gently on the tides. You can't see it right now, lying here in the dark, but it's there. Somewhere above you, hidden by clouds or daylight or the curve of the earth, the moon is following its slow, patient orbit, as it has for billions of years, and as it will for billions more. Let that image settle with you. The moon, distant and unchanging. A quiet companion in the night. Or let it go. Either way, you're held by the same gravity, the same gentle force that shapes the cosmos, that keeps planets in orbit and galaxies together, and that, in its own small way, connects you to everything else. Let yourself sink deeper now. Let the words fade into the background. Let your awareness narrow and soften until all that's left is breath and warmth and the quiet presence of rest. We're almost there. Just a little further, and then you can let go completely. Let's talk now about the spaces between things. The voids. When astronomers map the distribution of galaxies across the universe, they find that most of the volume of space is nearly empty. These regions are called cosmic voids, and they can span hundreds of millions of light years across. Within them, there are very few galaxies, very few stars, just thin wisps of gas and the ever-present dark matter stretched thin across the emptiness. These voids aren't truly empty, of course. Nothing in the universe is truly empty. There are still atoms drifting through them, a few particles per cubic meter, maybe less. There's still the faint glow of the cosmic microwave background, filling all of space with its ancient light. And there's still dark energy, quietly pushing space apart, making the voids grow larger and emptier as time goes on. But compared to the bright filaments and clusters where galaxies gather, the voids are silent. They're the quiet spaces in the cosmic web, the pauses between notes in a long, slow song, and in some ways, they're the most honest representation of what the universe truly is. Mostly space, mostly nothing, with occasional islands of matter and light scattered through the vastness. It's a humbling thought. We live on one of those islands, a small rocky world orbiting an ordinary star in the outer arm of a spiral galaxy, which itself sits on the edge of a filament in the cosmic web. Most of the universe is elsewhere. Most of it is empty. And yet here we are, in this tiny pocket of density and warmth, looking out at the darkness and wondering what it all means. Maybe it doesn't mean anything. Maybe the universe simply is, without purpose or intention, just a consequence of physical laws playing out over billions of years. Or maybe meaning is something we create, something that emerges from our awareness, our ability to look at the stars and feel wonder, to contemplate the voids and feel a kind of quiet awe. Either way, you're here, and the universe is here, and for now, that's enough. Let your thoughts drift toward those voids now. Imagine yourself floating in one of them, far from any galaxy, far from any star. Just you and the darkness and the faint glow of distant light. So far away it's almost invisible. There's no sound, no wind, no sensation except the gentle awareness of space around you, vast and patient and still. You don't need to stay there long. Just let the image pass through your mind, a moment of stillness in the midst of everything else. and then let it fade and come back to yourself, lying here, breathing slowly, drifting closer and closer to sleep. Now let's think about the future. Not your future, but the future of the universe itself. We've already touched on this, but it's worth lingering on because the future is so vast, so unimaginably long, that it makes everything else seem brief by comparison. Our entire recorded history, all of human civilization, is just a few thousand years. The Earth has existed for about 4.5 billion years. The universe is nearly 14 billion years old, but the future, the time that lies ahead, could stretch on for trillions of years, or even infinitely, depending on how the universe evolves. For the next few billion years, things will continue much as they are now. Stars will keep forming, though more slowly than before, as the supply of gas runs low. Galaxies will keep colliding and merging. Black holes will keep growing, and the universe will keep expanding, gently and steadily, driven by dark energy. But eventually, things will start to change. Star formation will slow and then stop altogether, as the last clouds of hydrogen are used up or blown away. The stars that remain will age and die, one by one. The massive ones will explode in supernovae or collapse into black holes. The smaller ones will fade into white dwarfs, dense cooling embers that no longer burn. Over time, even those white dwarfs will cool and dim, becoming black dwarfs, invisible remnants drifting through the dark. Galaxies will grow darker as their stars burn out, and the universe will become a colder, quieter place, lit only by the occasional flicker of radiation from black holes or the faint afterglow of ancient light. This process will take an unimaginably long time. Trillions of years, maybe 100 trillion years or more. But eventually, the last star will burn out, and after that, the universe will be dark. But even then, it won't be over. Black holes will still exist, and they'll still be evaporating, very slowly, through Hawking radiation. A black hole the mass of the Sun would take about 10 to the 67 years to evaporate completely. Larger black holes take even longer, but given enough time, even they will fade away, releasing their mass and energy back into space as particles and radiation. And after the black holes are gone, what's left? Mostly just photons, particles of light, and perhaps some exotic particles like neutrinos, all drifting through an ever-expanding universe. The density of matter will be so low, and the distances so vast, that particles might go for billions of years without encountering anything else. The universe will have reached a state called heat death, a condition of maximum entropy, where no organized structures remain, and no energy is available to do work. It sounds bleak, maybe, when you describe it that way, but it's also strangely peaceful. A universe at rest, finally, after billions and billions of years of motion and change. No more explosions, no more collisions. Just the slow drift of particles through infinite space, cooling gradually toward absolute zero as time stretches on without limit. Some physicists speculate that even this might not be the end. Maybe after an unimaginably long time, quantum fluctuations could give rise to new structures, new pockets of low entropy, even new universes, or maybe the universe will simply continue as it is, empty and dark and still, forever. We don't know. And in a way, it doesn't matter. The future is so far away, so disconnected from anything we can experience or imagine, that it might as well be a different universe entirely. What matters is here, now, this moment, this breath, this quiet drifting towards sleep. Let your mind rest on that image for a moment if you like. A universe growing slowly darker and colder, not with violence or fear, but with a kind of gentle inevitability. And then let it go. Let the future stay in the future, unformed and unknowable, while you rest here in the present. Let's return to something closer again. The stars in our own galaxy. The Milky Way is a spiral galaxy, about 100,000 light years across, with a bright central bulge and several long arms spiraling outward. Our sun is located about halfway out from the center, in a relatively quiet region between two major arms. We orbit the galactic center once every 230 million years or so, a period sometimes called a galactic year. In the center of the galaxy, things are more crowded. Stars are packed more densely, and there's a supermassive black hole, about 4 million times the mass of the sun, sitting quietly at the very heart of the Milky Way. We call it Sagittarius A star, and while it's massive, it's also relatively inactive right now. It doesn't seem to be consuming much matter, so it doesn't glow brightly like some other galactic black holes. But it's there, a dark anchor holding the galaxy together, surrounded by dense clusters of stars that orbit it in tight, fast ellipses. Some of these stars complete an orbit in just a few years, moving at incredible speeds, pulled by the black hole's immense gravity. Out here, in the quieter regions, things move more slowly. Stars drift along their orbits, interacting only rarely. Occasionally, two stars might pass close enough to perturb each other's paths, or a dense cloud of gas might trigger a burst of new star formation. But mostly, it's calm. Just the slow, steady motion of billions of suns, all orbiting together, held in a loose gravitational embrace. And scattered among those stars are planets. Billions of them, probably, maybe more. Some orbit close to their stars, scorched and airless. Others orbit far away, frozen and dark. A few, perhaps, orbit in that narrow band, where temperatures allow for liquid water, where chemistry can become complex, where life, if it arises at all, might have a chance. We've found thousands of these planets already, using telescopes that can detect the tiny wobble a planet causes in its star, or the slight dimming when a planet passes in front of the star's face. Each discovery is a small reminder that our solar system is not unique. There are other worlds out there, other possibilities, other stories waiting to unfold. Some of those worlds might be dead, lifeless rocks or clouds of gas. Others might be teeming with microbes, oceans full of simple life, ecosystems we can barely imagine. And a few, maybe, might have developed intelligence, built civilizations, looked up at their own night sky and wondered if they're alone. We don't know. We haven't heard anything yet. No radio signals, no messages, no signs of technology beyond our own. But the universe is vast, and our search has only just begun. Maybe life is rare. Maybe we're the only ones, at least in this galaxy, at least right now. Or maybe life is common. But intelligent life is fleeting, burning brightly for a few thousand years before fading away, leaving no trace. Or maybe they're out there, quiet and patient, listening just as we are, waiting for a signal that never comes. It's a strange thought, isn't it? That loneliness might be a cosmic condition, not just a human one. That across the galaxy, there might be countless worlds filled with life, all of them wondering if they're alone, all of them looking out at the stars and seeing only silence. But maybe silence is okay. Maybe it's even peaceful. After all, you're alone right now, lying here in the dark, and it doesn't feel lonely. It feels restful, safe, a chance to let go of the noise and the demands and simply be. Let that feeling settle over you now. The quiet of the night, the stillness of your body, the gentle rhythm of your breath. You don't need to search for anything. You don't need to find anything, just rest. Let's talk about neutrinos for a moment. Neutrinos are among the strangest particles in the universe. They're incredibly light, almost massless, and they barely interact with anything. Trillions of them pass through your body every second, coming from the sun, from distant stars, from the cosmic background, and you never feel a thing. They slip through atoms like ghosts, traveling at nearly the speed of light, crossing vast distances without slowing or stopping. Neutrinos are produced in nuclear reactions, the kind that happen in the cores of stars or in supernova explosions. When a massive star collapses, it releases an enormous burst of neutrinos, carrying away most of the energy of the explosion. These neutrinos can escape from the star's core long before the light does, because they don't interact with the surrounding matter. By the time the supernova brightens and becomes visible, the neutrino burst has already passed, spreading out through space at nearly the speed of light. We can detect neutrinos, but only rarely, and only with very sensitive detectors. Some are buried deep underground, shielded from other particles, filled with huge tanks of water or other materials. When a neutrino occasionally collides with an atom in the detector, it produces a tiny flash of light, which can be measured and recorded. These events are rare, maybe a few per day, but they're enough to tell us something about the neutrino's origins and properties. Neutrinos also carry information about the early universe. There's a background of neutrinos, similar to the cosmic microwave background, that was released about 1 second after the Big Bang. These relic neutrinos have been traveling through space ever since, cooled by the expansion of the universe, now moving at lower energies. We haven't detected them yet, but in theory, they're all around us, another faint echo of the universe's beginning. It's a quiet thought, that right now, as you rest, you're surrounded by particles from the earliest moments of time, streaming through you, invisible and untouchable, carrying the memory of a universe that was once unimaginably hot and dense, now cooled and expanded into the vast, gentle cosmos we see today. You don't need to picture this in detail. Just let the idea rest there. Neutrinos, ancient and silent, passing through everything, connecting the present to the distant past, and all of it happening without sound or sensation. Just the quiet flow of particles through space. Let's drift now towards something even more abstract, the nature of space itself. We tend to think of space as a stage, an empty backdrop against which events unfold. But according to general relativity, space is more than that. It's a dynamic entity, something that can bend and stretch and ripple. Mass and energy curve space. And that curvature is what we experience as gravity. When you fall, you're not being pulled by a force. You're following the natural curvature of space-time, falling along the straightest possible path through a geometry that's been warped by the Earth's mass. This is a strange way to think about things, and it's not intuitive. But it's been confirmed by countless experiments. Light bends as it passes near the sun, exactly as Einstein predicted. Time runs slower in strong gravitational fields. Gravitational waves, ripples in space-time itself, have been detected from colliding black holes and neutron stars. Space, in this view, is not empty. It's something, a fabric, a field, a structure that has properties and behaviors. And on the smallest scales, quantum mechanics suggests that space might be even stranger. Instead of being smooth and continuous, it might be grainy, made of tiny discrete units, like pixels in an image. This is the realm of quantum gravity, where our current theories break down and new ideas are needed. Some physicists think space might be emergent, not fundamental. In other words, space might be something that arises from deeper, more basic laws, the way temperature emerges from the motion of atoms, or the way wetness emerges from the interactions of water molecules. If that's true, then at the deepest level, the universe might not be made of space and time at all, but of something else, something we don't have words for yet. These are difficult ideas, abstract, and hard to grasp. But they're also strangely freeing. They remind us that the universe is not what it seems, that the solid, stable reality we experience every day is just one layer, one way of looking at things. Beneath it or beyond it, there might be depths we can't yet imagine. You don't need to understand any of this. You don't need to hold on to it. Just let it drift past another layer of mystery, another reminder that the cosmos is deeper and stranger than we know. And then let it go and sink a little further into rest. Now, let's think about light again, but in a different way. The light that fills the universe. Every point in space is filled with light. Photons traveling in all directions, coming from stars and galaxies, and the cosmic microwave background. Some of this light is visible, but most of it isn't. There are radio waves, infrared, ultraviolet, X-rays, gamma rays, all forms of electromagnetic radiation, all streaming through space at the speed of light. When you're standing outside during the day, you're bathed in light from the sun. But you're also bathed in light from distant stars, from galaxies millions or billions of light years away, from quasars and pulsars, and the faint glow of the Big Bang. All of it is arriving at your location, all the time, layered together, a chorus of photons from across the universe. Most of this light is too faint to see, too scattered to notice, but it's there. And if you had the right instruments, you could detect it, measure it, and trace it back to its source. Each photon carries a story, a record of where it came from and what happened along the way. Some have traveled for billions of years, crossing unimaginable distances, just to arrive here, at this moment, at this place. And then they're absorbed, their energy converted into heat or chemical reactions or electrical signals. The journey ends. The story closes. And the photon is gone. Its existence finished. Its purpose, if it had one, fulfilled. It's a gentle way to think about endings, not as loss, but as completion. The photon didn't fail. It simply did what it was meant to do. It traveled, it carried energy, and then it stopped. And in stopping, it became part of something else, part of the ongoing flow of energy and matter through the cosmos. Maybe that's how all endings are. Not failures or tragedies, but transitions. One form becoming another, one journey giving way to the next. In the vastness of time, nothing is ever truly lost. It just changes. Let that thought rest with you, or let it dissolve. Either way, you're moving closer to your own kind of transition, from waking to sleeping, from thought to dream, from the gentle flow of ideas to the quiet stillness of rest. Let's talk about the galaxies one more time. There are so many of them. Spirals like the Milky Way, with their graceful arms and bright central bulges. Ellipticals, smooth and featureless, filled with old red stars. Irregulars, chaotic and asymmetric, still forming stars at a rapid pace. And strange hybrids, galaxies that don't fit neatly into any category, shaped by collisions or interactions or processes we don't fully understand. Each galaxy is a world unto itself, a collection of billions or trillions of stars, bound together by gravity, drifting through space on its own unique trajectory. Some are active, with bright cores powered by supermassive black holes. Others are quiet, their black holes dormant, their star formation nearly ceased. Some are colliding with neighbors, their stars and gas mingling in slow-motion cosmic dances. Others are isolated, drifting alone through the voids, with no companions for hundreds of millions of light years. And all of them are moving, carried along by the expansion of space, receding from one another at speeds that increase with distance. The farther away a galaxy is, the faster it's receding, until eventually, at some enormous distance, galaxies are moving away faster than light, not because they're traveling through space at that speed, but because the space between us and them is expanding so quickly that light can never close the gap. This means that most of the universe is already beyond our reach. We'll never visit those distant galaxies. We'll never see them up close. Their light will continue to arrive for a while, stretched and dimmed by the expansion, but eventually, even that will fade, and they'll slip beyond the cosmic horizon, invisible and unreachable, forever separated from us by the relentless growth of space. It's a kind of cosmic loneliness, but it's also strangely peaceful. The universe is letting go, allowing things to drift apart, not out of cruelty or indifference, but simply because that's how expansion works. Everything moves away from everything else, slowly and inevitably, until each galaxy becomes an island, alone in an ocean of darkness. But that's far in the future. For now, galaxies are still clustered together, still interacting, still visible across billions of light years, and we can still look out at them, marvel at their beauty, and wonder what they might contain. Other stars, other planets, other possibilities, maybe even other minds, looking back at us, wondering the same things. Let yourself drift with those galaxies now. Imagine them receding slowly into the dark, not with fear or sadness, but with a kind of gentle acceptance. The universe is vast. Things drift apart, and that's okay. It's just the way things are. Let your breathing slow even more. Let your body soften completely. There's no tension left to hold. No thoughts left to follow, just the quiet awareness of breath and darkness, and the slow approach of sleep. Now let's think about the cosmic microwave background one last time. This is the oldest light we can see, the afterglow of the Big Bang, released when the universe was just 380,000 years old. It fills all of space, a faint glow at a temperature of about 2.7 degrees above absolute zero. It's been traveling for over 13 billion years, stretched by the expansion of the universe from visible light into microwaves. When we map this light, we see tiny variations in temperature, differences of only a few millionths of a degree. But those variations are incredibly important. They're the seeds of structure, the slight differences in density that would eventually grow into galaxies, clusters, and the cosmic web. Without them, the universe would be perfectly uniform, and nothing interesting would ever happen. No stars, no planets, no life. The cosmic microwave background is also remarkably uniform. When you look at it from different directions, the temperature is almost exactly the same, to within 1 part in 100,000. This uniformity is one of the main pieces of evidence for cosmic inflation, the rapid expansion that happened in the first fraction of a second after the Big Bang. Inflation stretched the universe so quickly that regions which started out close together, and therefore at the same temperature, were pulled far apart. That's why the whole sky looks so similar, even though light hasn't had time to travel between the most distant parts since the Big Bang. But there are anomalies. Small features in the cosmic microwave background that don't quite match our predictions. A cold spot, larger than expected. An asymmetry, where one side of the sky looks slightly different from the other. These anomalies might be nothing, just random fluctuations, statistical noise. Or they might be hints of something deeper, something we don't yet understand. Perhaps the imprint of another universe, colliding with ours during inflation. Or perhaps a sign that our models are incomplete, that there's more to the early universe than we know. We don't have answers yet, and maybe we never will. The cosmic microwave background is a snapshot of the universe at a single moment in time, frozen and unchanging. We can study it, map it, analyze it, but we can't go back and see what happened before. The earlier moments, the first fractions of a second, are hidden from us, veiled by the hot, opaque plasma that filled space before the universe became transparent. But even without complete answers, the cosmic microwave background is beautiful, a relic of the beginning, a faint echo of the moment when the universe first let light travel freely. And it's all around you, even now, passing through the walls, through your body, as invisible and untouchable as neutrinos, carrying the memory of a time before stars, before galaxies, before anything we would recognize as structure. Let that image rest with you. The universe, young and hot, and glowing, slowly cooling and clearing, until light could finally stream through the darkness. And that light, ancient beyond imagining, still traveling, still carrying its message, still filling space with its gentle presence. You can let it go now. Let the cosmic microwave background fade into the darkness behind your eyelids. Let the early universe dissolve into the quiet present. And let yourself drift, unmoored from time, from space, from thought. Let's talk about entropy for a moment. Entropy is a measure of disorder, of how spread out and disorganized energy is. The second law of thermodynamics says that entropy always increases, or at least never decreases, in a closed system. Things tend to spread out, to even out, to lose their structure. This is why heat flows from hot to cold, why gas expands to fill a room, why ice melts and doesn't spontaneously refreeze. It's also why the universe is evolving the way it is. From a hot, dense beginning to a cool, diffuse future. Entropy is increasing, slowly but steadily, as energy spreads out across ever larger volumes of space. In the far future, when stars have burned out and black holes have evaporated, the universe will have reached a state of maximum entropy. Energy will be distributed so evenly and so thinly that no organized structures can form. No stars, no galaxies, no life. Just particles drifting through space, carrying tiny amounts of energy, with nothing to distinguish one region from another. This is sometimes called the heat death of the universe, though it's not really a death in the usual sense. It's more like a fade, a slow transition from complexity to simplicity, from order to disorder. And it's not something to fear, because it's so far in the future and so gradual that it's almost abstract. By the time the universe reaches maximum entropy, everything we know, everything we care about, will be long gone, transformed beyond recognition by the passage of unimaginable amounts of time. But entropy is also the reason you're here. The universe started in a state of incredibly low entropy, with all its energy concentrated in a tiny, hot region. As it expanded and cooled, that energy spread out, but not uniformly. Slight variations, quantum fluctuations, created pockets of higher density, which collapsed under gravity to form stars and galaxies. And stars, burning through nuclear fusion, create even more entropy, releasing heat and light into space, spreading energy outward. Life, in a way, is a process of creating entropy. You eat food, which contains organized chemical energy, and you use that energy to move, to think, to stay warm. In the process, you release heat into your surroundings, increasing the overall disorder. You're part of the universe's slow drift toward equilibrium, contributing in your own small way to the increase in entropy, but that doesn't make life meaningless. If anything, it makes it precious. You're a temporary eddy in the flow of energy, a brief moment of complexity in a universe that's slowly becoming simpler. And in that complexity, there's awareness, experience, the ability to wonder and feel and rest. That's not nothing. That's everything. Let that thought settle gently. You're part of the flow, part of the universe's long, slow journey from order to disorder. And for now, for this brief moment, you get to be here, conscious and breathing, before entropy carries you onward, transforms you into something else, returns your atoms to the cosmos from which they came. It's okay. It's all okay. Just let yourself drift with it, like a leaf on a stream, moving gently downstream toward whatever comes next. Now let's think about the cosmic web one more time, but from a different perspective. The cosmic web is not just a structure in space. It's also a structure in time. The filaments and clusters we see today didn't always exist. They formed gradually, over billions of years, as dark matter clumped together and ordinary matter followed. And they're still evolving, still changing. As galaxies merge and clusters grow and voids expand, if you could watch the universe and fast forward, speeding through billions of years in a few minutes, you'd see the cosmic web emerge from nearly uniform darkness. Tiny fluctuations would grow into filaments. Galaxies would light up along those filaments, like streetlights turning on at dusk. Clusters would form where filaments intersect, growing brighter and denser over time, and the voids would grow larger and emptier as matter drained out of them into the surrounding structure. It would look almost organic, like a living system growing and evolving. But it's not alive, not in any biological sense. It's just gravity, patiently pulling matter together, shaping the universe on the largest scales. And if you kept watching into the far future, you'd see the cosmic web slowly dissolve. Galaxies would drift apart, carried by the expansion of space. Filaments would stretch and thin. Clusters would evaporate as their member galaxies recede beyond each other's gravitational reach. And eventually, the web would fade entirely, leaving only isolated galaxies, or even isolated stars, drifting alone through an ever-expanding void. But that's trillions of years away. For now, the web is still here, still visible, still holding the universe together in its loose gravitational embrace. And you, on your small planet, in your small galaxy, are part of it. Connected, however tenuously, to everything else. Let yourself feel that connection now, if you like. Not as something you need to hold on to, but just as a quiet awareness. You're part of the web, part of the structure, part of the universe, looking back at itself, and then let that feeling dissolve and sink a little deeper into rest. Let's talk about Andromeda one more time. Andromeda is the nearest large galaxy to the Milky Way, about 2.5 million light years away. It's a spiral galaxy, similar to ours, but slightly larger, with perhaps 1 trillion stars. On a clear, dark night, you can see it with the naked eye, a faint smudge of light in the constellation Andromeda. It's one of the most distant objects visible without a telescope, and the light you see from it left Andromeda long before humans evolved, traveling for millions of years to reach your eyes. Andromeda and the Milky Way are on a collision course. They're moving toward each other at about 110 kilometers per second, and in about 4 billion years, they'll begin to merge. The collision will be slow and graceful. Stars are so far apart that actual collisions between individual stars will be incredibly rare. Instead, the two galaxies will pass through each other, their shapes distorted by gravity, stars and gas pulled into long tidal tails and streams. Over time, perhaps 1 billion years or more, the two galaxies will spiral around each other, losing energy through gravitational interactions until they finally merge into a single larger galaxy. Astronomers sometimes call this future galaxy Milkomeda a blend of the two names. It will likely be an elliptical galaxy, no longer a spiral, filled with older red stars and very little new star formation. By the time this happens, the sun will be nearing the end of its life. It will have swelled into a red giant, engulfing the inner planets, possibly including Earth. The night sky, if there's anyone left to see it, will be unrecognizable, filled with unfamiliar stars, new constellations, and perhaps a bright core where the two supermassive galaxies have merged. But that's so far in the future that it's almost like a different universe. For now, Andromeda is just a faint glow in the night sky, a distant neighbor slowly approaching, but still millions of years away from arrival. You can picture it if you like. Two galaxies drifting toward each other through the dark, moving so slowly that billions of years pass between each small change. Or you can let the image fade and simply rest in the knowledge that even on cosmic scales, things are always in motion, always changing, always moving towards some future we can barely imagine. Let your body relax even more now. Let every muscle go soft. Let your jaw unclench, your shoulders drop, your hands open. There's nothing to hold, nothing to carry, just the gentle weight of your body, sinking into the bed, supported and safe. Now, let's drift toward the question of consciousness. What is it that makes you aware? What is it that's experiencing this moment? Hearing these words, feeling this quiet drift towards sleep. Scientists and philosophers have puzzled over this for centuries, and we still don't have a complete answer. Consciousness seems to arise from the brain, from the complex interactions of billions of neurons, firing in patterns that somehow give rise to thoughts, feelings, and awareness. But how that happens, the exact mechanism, is still a mystery. We can map the brain, measure its activity, even predict some of its responses, but we can't fully explain why there's something it feels like to be you, why there's a subjective experience at all. Some think consciousness is an emergent property, something that arises when information is processed in certain complex ways. Others think it might be more fundamental, a basic feature of the universe, present in some form even in simple systems. Still others think it's an illusion, a story the brain tells itself, with no deeper reality. We don't know. And maybe we can't know, at least not yet. But what's clear is that consciousness, whatever it is rare and precious. As far as we know, most of the universe is not conscious. Stars burn without awareness. Galaxies spin without thought. Black holes consume without experience. Only in certain rare pockets, on certain small planets, under certain specific conditions, does matter organize itself in such a way that it becomes aware of itself. You are one of those pockets. A small region of the universe that has woken up, that can look around and wonder and feel. And for a brief moment, cosmically speaking, you get to experience this. The warmth of a bed, the darkness of a room, the quiet flow of thoughts and images, the gentle approach of sleep. It won't last forever. Consciousness, like everything else, is temporary. One day, your neurons will stop firing, your thoughts will cease. And whatever it is that makes you, you will dissolve back into the universe, your atoms scattered, your patterns lost. But that's okay, you're here now. And now is enough. Let that settle gently. You don't need to fear the end. You don't need to grasp at permanence. Just be here. For as long as you're here, and let the rest take care of itself. Let your awareness narrow now. Let it focus on just your breath, slow and steady, in and out, or let it expand until it feels like you're floating in darkness, with no boundary between yourself and the space around you. Either way is fine. There's no right or wrong. Just the gentle drift, the quiet letting go. Let's talk about the Planck scale one more time. This is the smallest scale at which our current understanding of physics makes sense. It's about 10 to the minus 35 meters, unimaginably tiny, far smaller than an atom, smaller than a nucleus, smaller than any particle we can detect. At this scale, quantum effects become so strong that space and time themselves might break down, becoming grainy or foamy, fluctuating wildly from moment to moment. We can't observe the Planck scale directly. We don't have instruments sensitive enough, and we probably never will. But theorists can speculate, using mathematics and thought experiments, about what might happen there. Some think space might be made of tiny discrete units, like pixels in an image. Others think it might be a web of quantum loops, constantly forming and dissolving. Still others think the whole concept of space might be emergent, something that only appears at larger scales, with something else, something stranger, underlying it. These ideas are far from proven, and they might never be testable, but they're beautiful in their own way, attempts to describe reality at its deepest level, to peer into the foundations of existence and see what's really there. And what's remarkable is that these tiny, quantum-scale fluctuations might be connected to the largest structures in the universe. During cosmic inflation, quantum fluctuations at the Planck scale were stretched to cosmic proportions, becoming the seeds of galaxies and clusters. In this way, the smallest and largest scales are linked, part of the same unfolding story. It's a humbling thought that the universe contains such extremes, from the Planck length to the cosmic horizon, from quantum foam to galactic superclusters, and that somehow all of it fits together into a coherent whole. You don't need to understand it. You don't even need to think about it. Just let it rest there, another layer of mystery, another reminder of how deep and strange reality is, and then let it fade and drift a little further into the quiet. Let's think about the stars one more time, but differently now. Each star is a sun. Each one could have planets, could have worlds, could have life. When you look up at the night sky, you're not just seeing points of light. You're seeing possibilities. Countless possible stories playing out across the galaxy, most of which we'll never know. Some of those stars have already died. Their light is still traveling toward us, but the stars themselves have burned out, collapsed, exploded, or faded away. We're seeing their ghosts, images from the past, still shining across the void. Other stars are being born right now, forming in dense clouds of gas and dust, igniting for the first time, beginning their long, slow burn. By the time their light reaches us, millions of years from now, they might be old, red, fading, or they might be gone entirely, and still other stars haven't been born yet. They'll form from clouds that are still diffuse, still cold, still drifting through the galaxy. Billions of years from now, they'll ignite, shine, and eventually fade, all of it happening long after our sun has died. The night sky is not a static picture. It's a flowing river of time, with light from different eras all arriving at once, layered together, creating the illusion of a single moment. But really, it's countless stars at countless stages of their lives, all sending their light outward, into the dark. You're part of that flow, too. Your light, the warmth you radiate, the energy you give off, it's all flowing outward, mixing with everything else, becoming part of the background hum of the universe. You're not separate. You're woven in, connected, part of the same vast pattern. Let that thought rest lightly, or let it go entirely. Either way, you're held. You're part of something larger. And that something larger is holding you gently as you drift towards sleep. Now, let's return to dark matter one last time. We still don't know what it is. Decades of searching, and we still haven't found a single dark matter particle. Detectors deep underground have been running for years, waiting for a collision, but so far, nothing. Or at least, nothing we can confirm. It's frustrating, in a way. To know that something is there, to see its effects so clearly, and yet not be able to touch it, to measure it, to understand it. But it's also a reminder of how much we still have to learn. The universe is not finished revealing itself. There are still mysteries, still questions, still dark corners waiting to be illuminated. And maybe that's okay. Maybe not knowing everything is part of the beauty. It leaves room for wonder, for imagination, for the quiet thrill of discovery. And it reminds us that we're not the end of the story. We're just one chapter, one small part of a much longer journey. The search for dark matter continues. New detectors are being built, new theories are being tested. And someday, maybe soon, maybe not for decades, we'll find it. We'll finally understand what makes up most of the mass in the universe. And that will be a beautiful moment, a quiet triumph of patience and persistence. But even if we never find it, even if dark matter remains forever beyond our reach, it's still there, still holding galaxies together, still shaping the cosmic web, still drifting silently through you, invisible and untouchable, a reminder that the universe is filled with things we cannot see, cannot measure, and perhaps cannot understand. Let yourself drift with the dark matter now. Let it pass through you, silent and unnoticed. Let it carry you gently, like a current in a vast, invisible ocean, pulling you deeper into rest. Your breathing is very slow now, very soft, each breath longer and deeper than the last. You can feel yourself sinking, not just into the bed, but into something deeper, into stillness, into quiet, into the dark. Let's talk about silence. Space is often described as silent, and it's true. There's no air to carry sound, no medium for vibrations to travel through. But that doesn't mean space is empty of activity. Stars pulse, black holes emit radiation, galaxies collide. All of it happens in silence, at least the kind of silence we can hear. But there are other kinds of sounds, if you broaden the definition. Gravitational waves, for example, are sometimes described as sounds. When two black holes merge, they send ripples through space-time. And those ripples have a frequency, a pitch, a rhythm. Scientists have converted these gravitational waves into audio, creating a kind of cosmic music, a deep, rising chirp that represents the final moments of a collision billions of years ago. And stars vibrate too, oscillating with pressure waves that move through their interiors, creating frequencies that can be detected and measured. This is called astroseismology, the study of stellar vibrations. Each star has its own unique set of frequencies, like a musical instrument, and by listening to these vibrations, scientists can learn about the star's internal structure, its age, its composition, In a way, the universe is full of music. Not the kind you can hear with your ears, but the kind you can detect with instruments, translate into data, and then, if you choose, convert into sound. It's a quiet music, slow and deep, playing out over timescales of millions or billions of years. But it's there, always there, if you know how to listen. And even the silence itself is not really silence. The cosmic microwave background, the faint hum of the Big Bang, is sometimes described as a kind of static, a background noise filling all of space. It's not loud, and it's not in a frequency we can hear, but it's there, a constant presence, like the sound of the ocean when you hold a shell to your ear. Let yourself listen to that silence now, not with your ears, but with your awareness. The quiet hum of the universe filling the space around you. Or maybe just the silence of your room, the stillness of the night, the soft absence of sound that means rest and safety and peace. Let it wash over you. Let it fill you. Let it carry you gently into the dark. You're almost there now, almost asleep. Your thoughts are fragmenting, dissolving into images and feelings, half-formed and fleeting. That's okay. That's how it's supposed to be. Just let them come and go, like clouds drifting across the sky, without holding on to any of them. Let's think about the future one more time. But not the cosmic future. Your future. Tomorrow will come. The sun will rise, whether you see it or not. The earth will keep turning. The stars will keep burning. And you'll wake up, rested and refreshed, ready for whatever comes next. But that's tomorrow. Right now, there's only this. This moment. This breath. This gentle drift into sleep. You've traveled far tonight, in your mind, if not in body. You've drifted through galaxies, floated through voids, brushed against black holes, and listened to the faint echoes of the Big Bang. You've touched, however lightly, the deepest mysteries of existence. And now, it's time to let all of that go. Let the universe take care of itself. Let the galaxies drift. Let the stars burn. Let dark matter flow and dark energy push, and time stretch on into the infinite future. None of it needs you right now. It will all be there tomorrow, unchanged and patient, waiting for you if you want to explore it again. But for now, just rest. Let your body be heavy. Let your mind be quiet. Let your awareness fade, like a distant star sinking below the horizon, until all that's left is darkness and warmth, and the soft, steady rhythm of breath. You're safe. You're held. You're part of something vast and ancient and beautiful. And right now, in this moment, that's all you need to know. Let the darkness close in around you, gentle and complete. Let the last thoughts dissolve. Let the last images fade. Let yourself drift, unmoored and weightless, into the deep, quiet ocean of sleep. The universe is still out there, vast and patient, spinning slowly through the dark. The stars are still burning. The galaxies are still drifting. And somewhere, in the midst of all that vastness, you are here, breathing softly, letting go, falling gently into rest. Let the cosmos hold you now. Let it carry you through the night, safe and still, until morning comes again. And if you're still aware, still listening, that's okay too. There's no hurry, no pressure. Just the quiet flow of time carrying you gently forward into whatever comes next. Sleep well, rest deeply, and know that when you wake, the universe will still be here, waiting patiently, full of wonder and mystery and light, ready to welcome you back whenever you're ready to look up at the stars again. And if you'd like to drift off to more stories like this, softly told, filled with wonder, consider subscribing. There's always more to explore, one sleepy soul at a time. Good night.